stands for Organic Light Emitting Diode, in which emissive layer is a film of organic compounds that emits light in response to an electric current. All these are used to create digital displays in devices such as television screens, computer monitors, portable systems such as mobile phones. A major area of research nowadays is the development of white OLED devices for use in solid-state lighting applications. Now, before delving into organic OLED, we will try to investigate briefly the conventional light-emitting diodes. If you take an N-type and the P-type semiconductor and place them side by side, you obtain a p-n junction diode. There exists a depletion region surrounding the physical junction due to the excess carriers in each half recombining with each other. This leaves behind an unionized mobile atoms that create an electric field which opposes further carrier diffusion and drives Hall drift in the direction of the field. When the P material is placed at a higher voltage than the N material, the diode is then in the forward bias, and the carriers overcome the internal fields of the depletion region to diffuse, which sets up a current from the P side to the N side. Now, we have seen how a diode looks like, and now let's delve into the band diagram with no bias applied. We will observe that the Fermi level is constant and far from the band edges. This means that few carriers will cross the valence to the conduction band. Meanwhile, when a positive bias is applied to the P side, as in the current drawing, the potential difference is lowered between the two sides. This is demonstrated by the lesser slope in the Fermi levels of each side, and they are no longer equal. They are called quasi-Fermi levels. This leads to the Hall diffusion into the N side. Looking back, we will see that one holes diffuse into the N side and they will combine with electrons to lower the overall energy of the system and release photons. These photons represent the light we see. Take a look at organic LEDs. Instead of p-doped and n-doped semiconductors, organic LEDs are made up of multiple layers. The top and the bottom, called the seal and substrate, respectively, are usually made of glass or plastic, and they serve to protect the rest of the device. Below the seal is the cathode, or negative terminal. Underneath is the emissive layer, where the light is produced. Next, we have the conductive layer, is the source of the LED charge carriers, either electrons or holes. The middle two layers are organic polymers, and they are capable of conducting electricity. During operation, voltage is applied across the OLED, and this causes holes to be injected into the highest occupied molecular orbital or HOMO of the polymer within the conductive layer, and these holes can diffuse and recombine with electrons near the emissive layer, producing photons. And the frequency of the light is dependent on the difference of energy between the conductive layer polymers HOMO and the emissive layer polymers in the lowest unoccupied molecular orbital, or called LOMO. By combining thousands of individual red, green, and blue OLEDs, these will together function as pixels to create a high-resolution picture as we see in the high-technology televisions right now.